Good day. My name is Lara van Niekerk. I'm from the Council for Scientific and Industrial Research, and I will be giving you today a very brief introduction into environmental flows, some key concepts and methods that we use in South Africa, and also introducing you a little bit to the wider picture. Important biophysical processes in estuaries are driven by both river runoff and seawater intrusion, and this will be very different from what happens in river systems. And one of the key things we look at is the longitudinal gradients along our systems, both in salinity but also in other physical water quality parameters, which is all the way from upstream to the mouth of the estuary. There's marked differences in the chemistry between river water and seawater, and this has got a very strong influence on water quality. And by that, I don't necessarily mean pollution, I just mean the different water quality parameters in the system. What should also be known is that the physical characteristics and water quality in the system is not the result of a single event, but rather that of a flow pattern occurring over weeks and months. So we need to understand the changes as the river flow comes into the system, how the salinity gradient forms in the estuary, and what the influence of the sea is. And also how the estuary responds between strong river input when it's more fresh and even in the nearshore environment where we can detect the signal of fresh water. Also, a key concept to understand is that we follow a cascading approach in e-flows for estuaries, starting with understanding the flow patterns into our estuaries. The abiotic process is hydrodynamic, sediment dynamic, and water quality, and the impact it has on the biotic components, microalgae, macrophytes, inverts, fish, and birds. And in some e-flow assessments around the world, they've even looked at reptiles and mammals. Also important is the focus is often on the links between these, the link from flow to abiotic characteristics, and then from abiotic to biotic characteristics, and how the biotics responds to the abiotic characteristics. And then the ecosystem services and their overall response to this. How does flow changes drive the ecosystem services moving forward? In South Africa mostly, our biotic responses is microalgae, macrophytes, invertebrates, fish, and birds. I'm going to be using a paper that we published in 2019 that looks more on the science behind the process versus the actual steps in the flow requirement studies as delineated by the water affairs method. So the whole process starts off with understanding your hydrology and having a decent hydrological assessment of your flows done before the time. Once you understand how the flows have changed, by that I mean the base flows, the floods, intermediate flow signals, we then take it through understanding the abiotic processes and patterns and how they respond to flow. So we're going to look at delineating the estuary and zoning it, identifying abiotic states, understanding the annual distribution and how that's changed, and then linking that to the biotic responses. Then I'm also going to briefly talk about negotiating the future health of the system, where you look at the present health condition, the stresses on the system or the pressures, the importance of the estuary, and what future state we want it to be in. And then finally we do the flow allocation process. So talking first about hydrology and river inflow, you need to understand that flows regulate the melt state of our systems, whether it's open or closed, the link to the marine environment, and it also provides important cueing effects for migratory species such as fish and inverts. It regulates our salinity profiles in our systems, which is then strongly related to biological responses. It introduces nutrients into estuaries, And it also scours accumulated sediments during floods and prevents systems from not actually filling up. Understanding a little bit about what it means, for argument's sake here I'm going to be comparing a large catchment and a small catchment. In a large catchment, my example here is the Olifants catchment, a very large system, nearly 50,000 square kilometers. And what you can see is that in every winter, the base flows in the system actually lifts from an extremely low flow scenario where we can barely see the inflow of about 3 to 5 cubic meters per second, to 3 to 6 months of the year, it actually lives to, argument's sake, 20 cubic meters per second, which means that the salinity profile is consistently pushed back in winter for 3 to 6 months. If you compare that with a small catchment, in this case I'm using the Sahara estuary as an example, it's all of 18 square kilometers, the catchment. The first thing you can see is that the flow pattern is extremely irregular, with only a spat of a few days occurring at a time. So you can see you're getting a very different signal from a large to a small catchment, which in turn is driving very irregular responses in the two different estuarine systems. Once we understand the flow regime feeding into an estuary, we need to start thinking about what we're actually going to be evaluating, and that requires delineation and zonation of our estuaries, from the river reach through the estuarine system out to the sea. So in the case of an estuary, the upper boundary is as far as the tidal influence could be detected, or salinity intrusion in some cases. The lateral boundary is about the 5-meter contour, and it encapsulates the full tidal range, the areas that needs to be backflood, the 1 in 100-year flood line in other key biotic processes. And the seaward boundary in South Africa's case is generally the estuary mouth, but it can be extended out to sea. We have the methods and the abilities to do that. Once we understand the physical space in which we need to do the e-flow study, we will then look at zoning the estuary into more homogeneous regions. In this case, we use geomorphology and bathymetry, so shallow areas, deeper areas that have similar mixing processes. We look at the salinity regime in the systems and its responses to flow. And then finally, areas of high retention or low retention, because this can give you nonlinear responses. So in this example, the lower reaches might be frequently mixed by the tide and quite shallow. The middle reaches might actually be deeper and have some retention areas and even have stratification. And the upper reaches, which is a different zone, is mostly river dominated, very fresh most of the time, and shallow again. So the system will divide it into 3 equal zones to better understand the responses. In a complex system like a delta, we could even subdivide the system further into different regions. This is the example of zonation that was done in one of the larger delta systems. I'm just putting it up here to explain that zonation could be either very complex or very simple, depending on the system. Once we understand our system better, we also look at the pressures on the system. Anything from water quality, flow reduction, development, fishing pressures, pollution, artificial breaching, more development on the system. We also looked at past and present pressures. So in this case, there used to be a lot of beach driving occurring in some systems. That has largely been removed. But when we do e-flow assessments, we don't just look at present data, we also look at historical data. And you need to understand the timeline of how pressures has changed so that you contextualize any observations that's been made on the estuary over the last 50 or 60 years. Of special concern is not just flow changes, you've seen I've stressed this over and over, but also water quality. Water quality changes has been of significant concern of late, as it's driving change at regional scales. and it's something that's, especially in the case of estuaries, intrinsically linked to your flow requirement studies. So once we understand how a system functions and which parts are similar and which parts are different, we understand the flow changes in our system, we now start looking at grouping physical conditions together, which we call abiotic states. And in this example, I've got, for a system, 3 abiotic states that we've identified. The first one is when the estuary mouth is open and there's significant river inflow into the system and we've got good tidal exchange. The second state, we've got the sandbar at the mouth starting to develop, preventing significant tidal intrusion and with mostly river water coming into the system and flowing out to sea. And then finally, if the flow decreases even further, the estuary mouth closes and we don't have much input from the sea. So once we understand the flows, the areas of the estuary that works together, and we understand some of the key driving processes in the system, the next challenge is to link all of that to flows. Preferred method would be to use observed data and measured inflow to couple flows to states. If not, we will extrapolate from adjacent catchments. And finally, in the absence of anything else, we will use model data, which of course influences our confidence in the overall study. So in our example here, my first state is an open freshwater dominated state if the flows are more than 10 cubic meters per second. The second state is a semi-closed brackish state and the flows are between 5 and 10 cubic meters per second. And then finally, we've got a closed state indicated in red here when the flows are less than 5. Keep those colors in mind as well, please. So in our example, under the natural conditions, this is the flow range of the system. Flows, cubic meters per second, varying from 0 to 100 here. And this is January, February, March, our months at the bottom all the way to December. And what you can see in this system, in the winter months, basically the flows pick up enough that the system in its open freshwater dominated state for about 7 months of the year, while it is in the transition state semi-closed for about 2 months, here in March to April, and again here towards the end of December. And then finally, it's got a closed state for only about 3 months of the year under the natural conditions. Under the present day condition, in which there's been some dam development and base flow abstractions, we can now see both that the flow ranges are lower, but also what you'll notice here, where before we had the open freshwater dominated state occurring for about 7 months of the year, it is now occurring for only 4 to 5 months of the year. The transition states are still about 2 months of the year, and what you will see now is that the closed state is now starting to occur for about 5 to 6 months of the year. So the closed state is actually increasing and the freshwater dominant state is decreasing. And then finally, in our future development scenarios in which more dams got added to the system, we now have the state 1 of freshwater dominated open system only occurring for about 2 months of the year, our transition states occurring still for about 2 months, and the rest of the time the system is actually state 3 predominantly closed. So once we understand how the flow ranges is going to drive the mouth states, we use the Estuary Health Index to score the condition of the system. I will refer you back to Susanne's talk. Susanne Taljaard gave us a presentation on the Estuary Health Index, and I'm not going to go into detail in that today, except to say that that is basically those 3 scenarios that I've just discussed. They are scored through the Estuary Health Index and then rated relative to natural. So once we better understand the system, we then start looking at the present day condition, the importance of the system and its desired condition. And importance can relate to the biodiversity importance of the system. It can be the conservation importance of the system. It can be the importance of the system in terms of its ecosystem services, or even cultural importance. In South Africa, we mostly use biodiversity importance and conservation importance as the two deciding factors. And then finally, that together with understanding the present pressures on the system, we can define its desired condition, and then finally do the follow allocation that will keep it in the condition we want it to be. So it's basically a matrix that's used. If the system is highly important and it's in a natural or near natural state, we just need to maintain that condition. But if the system is already moderately modified at a C, then it needs to be improved to an A or a B. And if it's heavily modified, you need to bring it to an A or a B, or if we cannot do anything, best obtainable state. If it's just important, then our objective is to at least have a C condition in the system. And if it's of low to average important, the minimum state it can be in is a D. And as I said before, anything less than that, we have to try and improve the condition of the estuary to the best obtainable state. So those are our guidelines. It does not necessarily mean we'll achieve it, but the objective of the flow requirement study is to see how close as possible we can get to those states, and which flow scenario will actually allow us to maintain it in the desired condition. So in the case of our example that we had earlier, where we have this absolute decrease of the state 1 open system to something that is predominantly a closed state, if we had the objective of maintaining the present health of the system or even to increase its condition, then this scenario will be unacceptable. And the development would not be recommended by the flow requirement study. It also should be noted that our e-flows processes in South Africa very seldom happens anymore in estuary by estuary type of setting. We now have moved into the process of classification, which is a consultative process in which allowing stakeholders to negotiate the level of utilization of water resources in a catchment or region. The process includes rivers, estuaries, wetlands, and groundwater, and parallel to the flow requirements, in this case the estuaries, the rivers, the wetlands, there's also socioeconomic evaluation that's done looking at ecosystem services, macroeconomics, job creation, and actually infrastructure cost. And then all of this goes into a weighting scheme, which finally gives us the optimum development scenario for that estuary. So it's a very similar process to what I've just explained to you, except that it's done in all the legs of the different components. And then once we've decided on the optimum development scenario, we can also give you the target ecological condition, the resource quality objectives of the system, and provide some use limits. I'll just give you a brief example of what I mean by resource quality objectives. Here I'm going to give you a brief example of what we mean by a resource quality objective. These are stated in two different ways. The first is the ecological specification, how we want it to be. The second one is thresholds of potential concern. When will we start worrying if we exceed these values? Two examples here, the salinity is abiotic and fish for biotic. And so our ecospec is basically that we want the salinities to support the biotic assemblage in the system. So when will we worry if the salinity is higher than 20 parts per thousand for longer than 3 months, 7 kilometers upstream from the mouth? Or if the salinity is above 10 at about 16 kilometers upstream of the mouth. In the case of the fish, We first state what we want. We want the estuary species abundance between 30 and 40%, and the estuarine-associated marine species between 60 and 70%, and the indigenous species population should be roughly about 1%. In terms of thresholds of potential concern, we will be worrying first if the marine species in the system drop less than 50% of total abundance. But we will also be worried if the estuarine species above 50% of total abundance, or if there's occurrence of alien freshwater species in the system. So we're worrying if we're seeing clarias or tilapia or something occurring in the estuary. Finally, we also provide some indication of monitoring. So we're not only telling them in the Inflow study exactly what we want for the estuary, but also how we should be checking that we're receiving it. There should be, in this case, salinity, longitudinal salinity profiles taken in the system. It should be taken quarterly, and it should cover the whole estuary with at least 10 stations along the length of the system. In the case of fish, so we want to record the species and their abundance. We use gill nets and seine nets. It needs to be a summer and winter survey every 3 years. It must cover the entire estuary, and there must be at least 5 stations. So we provide some sort of an indication of how we want the system to be monitored. I would be amiss if I don't also stress that we have a flow requirement for the coastal and nearshore environment. I'm showing here a lovely picture of the Nzimvubu plume with all that fresh water and sediments flowing into the ocean. And I'm thanking Darren here for this beautiful picture showing this phenomena. In terms of that, fresh water flowing into the sea and coastal environments are not wasted. They provide important sediment supply to our beaches. They sustain our nearshore marine habitats. They cause a turbidity front, salinity fronts. They're bringing in all kinds of nutrients into our systems. The negative is that they also provide pollutants into sometimes quite high retention environments like bays. But all around, they have a function and role in the nearshore environment. They also kickstart a lot of biological important processes, like providing key habitats, increasing productivity. They play a role in key life stages and also in our coastal fisheries. And here's a picture near the Tugela banks showing you the extensive land signal in the marine environment. So I want to highlight this, that quite recently there's been new guidelines published for environmental flows in the West Indian Ocean region. And these guidelines are stressing the importance of the nearshore environment. This is not something that's often been done in estuaries around South Africa, coastal environments. And so I see this like the new frontiers for us and what needs to be studied moving forward. We've only ever done this for 2 systems in the country. The one is the Tugela, the other one is the Orange. But there's a significant amount of other river systems that need this type of flow requirement also applied to it. I would also just like to highlight some important literature that's been published in the last 5 years on this. The first 2 is the environmental flows method, the detail that I took you through earlier, looking at the method and integrating multi-scale eco-hydrological processes into complex estuarine processes. Then also the classification process, in which we show the links with the scenario based over a whole region and not just looking at a specific estuary. Janine Adams and I published on 10 key principles to keep in mind when we do environmental flows in temporary open and closed systems. There was the countrywide health assessment, which is using the index to understand changes, amongst others, flows. And then Susan Taljaard also published in 2017 on the screening model for water quality that we use, especially in small dynamic little estuaries in South Africa in the absence of anything else. There's more literature, so if you need to, you can contact me, but I think this will be a good start. And I wish you well if anybody wants to endeavor more research or get involved in future flow requirement studies. Thank you.